Hello everyone, welcome back to day 11 of Advent of Code, our second to last day. Today's problem is called Reactor and it goes the following way. You hear some loud beeping coming from a hatch in the floor of the factory, so you decide to check it out. Inside, you find several large electrical conduits and a ladder. Climbing down the ladder, you discover the source of the beeping, a large toroidal reactor which powers the factory above. Some elves here are hurriedly running between the reactor and a nearby server rack, apparently trying to fix something. One of the elves notices you and rushes over. It's a good thing you're here. We just installed a new server rack, but we aren't having any luck getting the reactor to communicate with it. You glance around the room and see a tangle of cables and a device running from the server rack to the reactor. She rushes off, returning a moment later with a list of the devices and their outputs, which is our puzzle input. For example, this is how our input looks like. So we have on the left, before our double dot or colon, we have our device and we have the outputs which says to which device is our device connected to which other devices is our device connected. The elves are pretty sure that the issue isn't due to any specific device, but rather that the issue is triggered by the data following some specific path through the devices. Data only ever flows from a device through its outputs. It can flow backwards. After dividing up the work, the elves would like you to focus on the devices starting with the one next to you. An elf hastily attaches a label which just says you, and ending with the main output to the reactor, which is the device with the label out. To help the elves figure out which path is causing the issue, they need you to find every path from you to out. In the example, these are all of the paths from you to out. Data could take the connection from you to BBB, then from BBB to DDD, then from DDD to GGG, then from G to out. Data could take the connection from B, then to E, then to out. Data could go from C, then to D, then to G, then to out. C, E out, C, F out. In total, there are 5 different paths leading from you to out. How many different paths can lead us from you to out? So this is a classic graph path finding problem. For this problem, we will be using a depth first search. And because finding every possible path from a starting node, which in this case is you, to the ending node, which is out, we will also be creating our algorithm, depth first search algorithm with memoization. How it will work is basically whenever we start from a certain neighbor, so let's say in this case we start from you. Whenever we finish checking the neighbors, the use neighbors, when we get how many paths we can get from our neighbors, we'll be storing that inside our memoization. So later on we can just access from inside the memo where we can check, okay, if our current vertex is inside the memo, then we don't need to again run our DFS algorithm over and over again, because we know how much then possible paths can lead from, for example, BBB or CCC. So how that would look like is the following. Of course, first we need to parse our input, and I guess I will just do like graph will be a dictionary. We will create our graph where the key will be a device and the value will be the neighbors the device is connected to. So we will just do open input example as F, and let me just change the number of spaces for Python like this for line in F, and we will do devices. I wanted to call it node, but to keep it up to the story we will call it devices. We will strip each line and we will split the line on the spaces. So then we will get like A, triple A, colon, U, and triple H as three individual devices. And then what we can do is graph. We can get our first devices, which is going to be the main device. We will of course strip out the colon. Is it colon or a double dot? I'm not sure. I guess I can say double dot because it's easier. And then we can just do devices or from the without the first element and then just everything else. How that would look like then, we can just do print our graph. There we have it. So our key here is like triple A, and the other neighbors are U and triple H. For U it's triple B and then triple C, and so on and so on. Now we can start writing our DFS algorithm, which will also include a memorization. So what we will do is the following. We will create a DFS, we will pass in a graph, we will pass in a current vertex, we will have a target vertex, and we will have a memo. This memo is basically gonna act like a, is gonna, well, be our memorization, where we will be storing all the, how many paths we can get for how many paths the current vertex had regarding its all neighbors, so we don't have to recheck it multiple times. So we just do if our current target, so this will be a recursive function. We need to have a break, which is if our current equals to our target, we will return 1, meaning this will return one valid path. And if we would have our current inside our memo of the current vertex, this will also be a dictionary that will store the key value paths. If we have it, we can just then return a memo of a current, because the key will be the vertex and the value here will be how many paths it has visited. Then we will just contain a variable called path count equals to 0. We will go for device in this case. Actually no, to keep it since it's a DFS, we can call it vertex in our vertex in graph of our, actually I'm gonna be using here get from current, and we'll give it a default value of an empty list. So what this get does is basically if we would access with a current, our current is going to be a key. If you would access into a graph and that key doesn't exist, for example, where is the out, since we don't have any device that is connected, we will get a key error. So this just says, okay, have a default value of an empty array. So let's start writing. For our vertex, we will just do path count plus an equals of DFS, where we will pass in the vertex. First we pass in our graph, pass in our vertex, target, and our memo. Oops. And all that is left to do is now to store our path count into our memo for the current vertex, and then we just return our path count. And that's basically it. What we are doing, once again, so let's say we start with this one. We have our current vertex, which is gonna be the U. We get a first access into the graph with that one, which happens here. And we get all the neighbors with this we get all the neighbors that are connected to the U, in this case triple B, triple C. And then we run our DFS again for those new devices or vertices, in this case, vertices. We run the pathfinding algorithm, and then if we have just reached the target, we return 1, then we just know we have successfully done this. Otherwise, we return 0 if nothing has happened. Now, what we can do is create a variable called total valid paths, which will equal to our DFS. We will pass in a graph. Our first starting node will be U, and our target node will be out, and we will pass in an empty graph as our memo object. And so what we just left to do is to print our answer. Part 1 will have total valid paths. If you run this, okay, so I'm now getting an error. Why is that? Oops, not like this in memo. Okay, and we get 5, which is the correct answer for the example input. And if I would run it on my example, I will get 749, which is the correct answer for my input. So let's start off with our part 2. Thanks in part to your analysis, the elves have figured out a little bit about the issue. They now know that the problematic data passes through both DAC, a digital to analog converter, and FFT, a device which performs a fast Fourier transfer. They're still not sure which specific path is the problem, and so they now need you to find every path from SVR, the server rack, to out. However, the path you find must also visit both DAC and FFT in any order. For example, now we have our new example input in this case. We don't have U anymore, so we need to be careful that when we are running our example input, we comment out the old code, and in this case, the old check, and in this case use the new one. This new list of devices contains many paths from SVR to out. And here's a list of how many paths contain FFT, DAC, or both FFT and DAC along its path. They say here, however, only 2 paths from SVR to out visit both DAC and FFT. Find all of the paths that lead from SVR to out. How many of those paths visit both DAC and FFT? So to solve this part 2, we will make some assumptions, but we will explain those assumptions later. How we would solve this is basically we would create a couple of paths that we can calculate, because it's simpler for us to create to break the calculation down into a sort of each own segment, rather than doing everything at once, searching any path with the given constraints. So they said that we need to come from SVR to up to out, and along our path we need to see either DAC, FFT to out, or we see FFT or DAC along the path in any order. So what we will do is we will create we'll calculate segment for SVR DAC, then we will create do for DAC FFT and FFT out, then we will do for SVR FFT, FFT DAC, and then DAC out. So how our code would look like for that is basically the following. Let's start with this one first. SVR DAC FFT out. So we do SVR DAC is gonna equal to DFS, where we pass in our graph. We have SVR starting node, DAC as the ending node, and we pass in empty memo. Then we have DAC FFT equals DFS a graph SVR, oops, it should be small, FFT, not SVR DAC. I'll just copy this. Then we have from FFT to out, FFT to out. Then we will have for SVR FFT, just gonna copy paste this. I'm gonna copy paste this one, put it down. FFT, why did I delete that one? DAC. And finally we have DAC out, which is going to be DAC out. So this is how it would look like now. So we will be so what we will do is we will be adding all of these together and adding all of these together and then multiplying them. Basically, it's part of combinatorics, which is where we have the addition rule and multiplication rule. In this case, we are chaining our segments, and we can then ask ourselves a question like, if there are x ways to do a task A and y ways to do task B, then we have x times y ways to do both of them. So we'll be adding these ones, and then we'll be multiplying them together. So it will basically be x times y, where this will be x and this will be y. We will soon explain what our assumptions are, but let's see first if this will work. We have named this total valid paths, but I will name this, I guess, like from U to out, and then we will name this total like valid paths SVR DAC FFT out, which will equal to SVR DAC plus DAC FFT plus FFT out, and valid paths, we will just swap these to out. We will just do SVR FFT plus FFT DAC plus DAC out. And what we will then just do is create a valid total valid paths from SVR to out, which is gonna equal to this times this. We will have part 2, and we will do this. Now, yes, I remembered I need to update my example. I didn't do that. Let me just get it from the Advent of Code. Have it here. Of course, I now need to comment out this one because U doesn't exist. But let's see if this will run. I won't run it yet for the main example, like that. We get 24, which is wrong answer. Why is that? So I just noticed that I explained the rule wrong about x and epsilon things. In this case, we need to be multiplying these ones. That was a huge oversight from my side. And then we add these ones to get the total amount of all possible solutions. And now this should equal to 2. This is our correct solution. So let's run this for our input now. Where is here? We do this, we do that, and if we would run this, we would get this huge number. That is the correct answer for my input. So I explained the rule wrong, but basically we have the first multiplication rule that says for our tasks A, there are x ways to solve them, and for task Y there are B ways to solve them. How many ways in total we have? So we just multiply like x times y. This is what we are basically doing here. There is that amount of possible segments where we can get like from SVR to DAC, DAC to FFT, and FFT to out, and so on and so on. And then we just combine our scenarios together. And these scenarios are, in this case, mutually exclusive. So the assumption we made here initially is that we have a directed acyclic graph, which in our case Basically what that means is that graph starts from one point and finishes on another point, and nowhere in between there exists a cycle that will keep repeating over and over again. Then to sort of come back to these rules, we have a multiplication rule, and then we have addition rule. For the multiplication, we know what we have said. We have, if there are x ways to do tasks A, to do task A, and if there are y ways to do task B, then total amount of those tasks is going to be x times y, or in this case we have 3 segments, then we just multiply them together. And then with the additive rule, we make an assumption also that the single path cannot be both scenario A, which in this case is gonna be a DAG first, or gonna be both scenario A, DAG first, and scenario B, FFT first, because these are mutually exclusive. So that's why we can add them. We also have one thing we can notice is how we had a lot of possible paths. I think I can showcase it like example. Not showcase because it will be 0, but we have a very high probability that one of our paths is going to be equal to 0, and one of our connected segments is going to be 0, because we have a directed acyclic graph. Because the assumption is like, if our data flows from SVR DAG FFT out, it cannot flow back from like SVR FFT DAG out. Maybe not from the start to the finish, but from DAG to FFT, and then it cannot flow back from FFT to DAG. Therefore, either one of our FFT or DAG is 0, or one of our DAG or FFT is 0. Okay, I think we can actually showcase that. I don't know why I said we can't. This is gonna show this. Where is the... Oh, I can just leave it. Cool. Let's print DAG FFT. So we see this one is 0, but let's see, print FFT DAG, which is gonna be equal to 1. So we know our data flows FFT DAG and not DAG FFT. So because of that 0, anything multiplied with 0 is gonna give us a 0. So that's basically it. I don't think there is anything more to explain. Tomorrow we are on our last day. I will try not to solve a test because I want to keep it sort of maybe special for the last day that we have. Why is this not running now? There we go. Try to keep it sort of special, so I will try to solve this as I'm making a video. Try to solve tomorrow's task as I'm making a video. So yeah, until tomorrow, I hope you guys have enjoyed this video and learned something. Any feedback is appreciated. Until tomorrow, as I have already said, enjoy your day and peace.